In this video, we are recapping the material that we learned from week 5 of Physics 259, where we relate our knowledge of electric fields, electric potential, and compare how electric potential behaves in insulators versus conductors. So the first topic we're going to talk about is electric potential of insulators. So some properties to note. So insulators don't allow free movement of electrons. Right, so once you have an insulating object charged with whatever you have with your electrons, they kind of just stay there. They're not stuck, so they're not free to move around, so they kind of just stay where they were initially brought to. So some materials, this is rubber. So just they don't conduct well. So this could also include plastic. This could include glass. Right? And those are just some examples of insulators. So this will start to make more sense in our later examples, but I also want to talk about our electric potential energy and to just give you a visual for how how you can think about it as a model. So we talked about that in our previous video. So if we were to hold two positive charges apart, they're going to want to go apart. But if we put a force there in this spring that forced it to keep together, this would cause positive energy. Right? So that means you have to add energy and you have to add and do work to keep them in this position. Because if this spring wasn't here, they would just go as far as they wanted away from each other. But since we're holding it with this spring is doing work to keep them closer together. So positive U is the energy that the charges would spring apart with if they were released. So since we're holding them in place with this spring, if we cut that spring out really briefly, then the energy that they would separate with is the same as our U. If we go to the next figure, so if we have an attractive force, right, so we have a positive and a negative charge, they would want to go together, right? But you have to push them apart and keep them away from each other, and that would mean doing negative work, because negative work was required to put the charges into that position. So it's similar to the repulsive force, except, I don't know, it's kind of like two friends that you have to separate because they like each other so much, right? That's a bad example. Never mind. So negative U is the energy that would be required to push the charges back to infinity. So that's the work that's required to put them as far away from each other as possible. So those are two different variations to think about, and I want you to notice that there are two charges now to consider. So the model that we're going to use for this example here, I'm just going to write this really quick. This is so we can represent this by U equals 1 over 4 pi epsilon 0 over charge A times charge B over separation of R. And you're going to think to yourself, wow, that kind of looks a lot like Coulomb's law. And you would be right, except our R is not squared in the bottom. So for this problem, we are asked to find the potential energy of the system. So what's the total energy? So if we did it to So we'll have to pair up these different charges, right? Because we want the work that each pair of charges exerts. So our combination, we can have 1 and 3. We can have 1 and 2. And we can have 2 and 3. So there's 3 different combinations. And if we add these all together, this gives us our total potential energy. So if we were to write that out, let's start with our U13. So this is our constant to start, and we have Q1, Q3, and our separation distance between them. Which is so this is d squared plus d squared, and this is equal to d root 2. Right, and if we plug those numbers in, this is 8.99 times 10 to the 9. This is Q1 is 5 nanocoulombs. And Q3 is also positive, so this is 4 times 10 to the 9. And already you can see this is going to be a positive value for our U because we have 2 positive charges to work with. And this separation of D is 0.1 meters, 2, and this is equal to so this is positive 1.27 microjoules, right? Units in joules because it's energy. And now let's do energy of 1 and 2. And this is just Q1 times Q2 over distance. And this is 8.99 times 10 to the 9 times 5 nanocoulombs. And now we have this negative. So when we do electrostatics, we usually don't consider our signs when we're calculating. But in this case, we would like to because we want to know if it's going to be overall positive or overall negative work. This is -7. And now I can see that this answer is going to be negative. And that makes sense because according to our example above, when we have attractive forces, we have negative U. And when we have repulsive forces, we have positive U. And that makes sense because we have a positive and a negative. This is 0.1 meters separation. And this is times 5 times 10 to the -9 times -7 times 10 to the -9 and divided by 0.1. This is negative 3.14 microjoules. Okay, and lastly, we have 2 and 3. And this is equal to, so we have a positive and a negative sign charge. So we can expect this to also be negative. This is 8.99 times 10 to the 9. This is 5 times 10 to the -9 and negative, oh, sorry, Q3. Q3 is 4, my bad. Times -7 nanocoulombs. And our separation distance is 0.1, so it's 8.99 times 10 to the 9 times 4 times -9 times -7 divided by 0.1. And this is negative 2.517 times microjoules. So we add them all up, we get So our positive was 1.27. Negative 3.14. And we have minus 2.517. And this gives us a total of, so that's 1.27 minus 3.14 minus 2.517. And this gives us negative 4.387 microjoules total. So biggest takeaway here is use charge signs. Okay, that's our first example done. Now with our second example, this is similar to what we did in our previous lectures. So we know that linear charge density is equal to Q over X length. And we know that to get Q, this is lambda times X. So to find our electric potential at a distance Z above our line of charge, we are going to use this equation here. Except instead, where R represents our separation distance along here. So if we rewrite this, this turns into, our dq turns into lambda dx, and our radius, sorry, not radius, our separation distance is equal to r squared plus z squared. Right, so if we write this equation, this becomes 1 over 4 pi epsilon 0 times lambda dx, and that's over our separation distance of x squared plus z squared. And in this example, we are varying the length of our x. So as we start from x equals 0 and measure it from x equals L, so these are going to be our integration limits. We can kick out the 1 over 4 pi epsilon 0 because that is a constant. So that leaves lambda dx over x squared plus z squared inside. And when we use an integration calculator, so just take my word for it, this gives us 1 over 4 pi epsilon 0 lambda ln L plus square root L squared plus x squared, sorry, z squared over z. Okay, so that's it for our second example. And for our next example here, this also brings us back to the lecture where we talked about the electric field produced by a disk. And we are using surface charge density. So we know that our surface charge density is equal to our charge over our area, which means that this is equal to our sigma times dA. Sorry, just regular A. So if we were to do the same thing again, we would do, so this is and this is times dq over our separation distance. So I'm going to draw our separation distance. And I meant to use red for this part. So if we do the same thing and replace them, you can kick out the 1 over 4 pi epsilon 0. And instead of our dq, we are going to be using surface charge density times our difference in area. And this is over our separation distance, which is r squared plus z squared. Oh, and this is still in our integral. And we are changing the limits of our big R. Right, so starting from 0 and as we increase our capital R. Sorry, I missed a couple intermediate steps along the way. Please bear with me. So instead of just saying instead of just saying A, we can make our Q equal to, so we have a disk, so that's the area of our disk, R squared, just R to the power of 1, dr. And this is going to go into our equation. So set up our bounds of capital R and 0, because as we change our capital R, that's what we want to see happen as we use infinitesimally small rings. So then this is 1 over 4 pi epsilon 0. In place of dq, we have sigma 2 pi r dr over separation distance of r squared plus z squared. So what can we cancel out? So we can cancel out this, turn this into a 2. To simplify it even further, so then this is going to give, so it's 2 epsilon naught sigma r dr for r squared plus z squared. And again, this is from r to 0. So we can kick out our constant. And when we integrate what is left in the integrand, this gives us our sigma over 2 epsilon naught and that is our square root of r squared plus z squared minus z. So this is our final answer to derive an equation for electric potential for a charged disk. Okay, so now we're going to talk about equipotential surfaces. So if you guys have ever seen a topographic map, that is a good way to imagine what this would look like. So a topographic map shows contours of a mountain where the concentric lines joining each other, right? So these kind of squiggly lines right here show parts of the mountain that have the same height. So the closer the lines together, the steeper they are. So this is basically just a bird's eye view of a mountain. So if you went up to a mountain and you drew a straight line all around the mountain at the same height, and you would do that at different heights, connecting them all together, that's what you would create using a topographic map if you saw it from above. So if I were to draw this mountain, it would look something like this. So starting from over here, right, it has a steady slope, and then it peaks up here. It's a little more steeper down, get a valley, and it's more flat here, and then it's much more pointy, so it's much more steep at the second slope, right? So you can imagine this mountain looking something like this. It's kind of a bad sketch, but you can imagine I guess, how that would work, right? So if we drew our topographic lines, you could expect them to look something like this. Right, so if you view it from above, that's what it would look like. It'd make those joining lines. So we can use this same sort of principle for equipotential lines, which are lines that connect points with the same electric potential to create a top-down view of how, I guess, particles are reacting with each other. So if we use this diagram here, where our positive charge is our green, our negative charge is our blue, you can imagine it creating lines that look like this. So those are kind of illustrated already, and the lines are a bit closer together at this end, and the same thing can be said for our positive. Right, so that's what each of these lines here are. So it's a bit difficult to see, but they are closer and steeper when they're closer together to each other. All right, and we know this is a positive charge because positive charges create kind of a peak, right, in a 3D space. You can imagine it looking like that. And our negative charges create wells, which is what this is. Because as you know, it flows high to low or positive to negative, right? That is how electric potential works. So you can imagine if you rolled a ball down the positive potential, it would roll down and into the negative, right? So it rolls from positive to negative. So V flows positive to negative. A property you should already know about electric potential. So in this example, let's calculate the electric potential of a dipole at the point labeled R in the drawing below. So if we started with our electric field, we'd say this is equal to 1 over 4 pi epsilon naught 2p y cubed, where p is our dipole moment from our previous lectures. And you know that to relate electric field to our electric potential is negative the integral of our electric field dot product with the path that it takes. So if we put our value for E in there, so this is 1 over 4 pi epsilon 0 to p over y cubed. And our bookend in this case would be dy because we are only traveling in the y direction along this axis. Okay, so this represents E here in blue. So we're going to kick out our constant. So this is negative 1 over 4 pi epsilon naught. We're going to integrate with bounds infinity to r to infinity, where r is our separation distance right here, and where y is the separation distance from r to the middle of our 2 points. So this is 2p over y cubed dy. We can also move this 2p out, so I'm just going to do that now, because that is going to remain constant as well. And that just leaves 1 over y cubed in the integral. If we integrate, this becomes negative 2p 4 pi epsilon naught, and that's 1 over y squared 2y squared. from r to infinity is equal to, so that's 1 over, it's negative 1 over infinity, because it's still going to be a pretty big number whether you multiply by 2 or not. And this is equal to plus, because it's minus minus, our 1 over 2r squared. Okay, so this is approximately 0, because if you have 1 over a really, really, really big number, that gives you a value that's close to 0. So we can take this infinity, cut it out, and we see that these are going to cancel. So then this becomes, so our v is then p over 4 pi epsilon naught times 1 over r squared. I'm going to move that p over, actually. Have these p and 1 change places. And our sign went away because we were measuring, so we're measuring 2-point-r from this direction. So because we're moving in this direction to measure, we measured from negative to positive. So because we went against the grain, that's why we started with this negative. But if we flip it, then we get our value for our positive electric potential. Okay, in our third example, now we're going to talk about electric potential of conductors. So some important things to note about conductors, this should be a review for you, is that they allow electrons to flow freely. So unlike our insulators, they don't become stuck once an object is charged. So because of this, charge distributes evenly on surface at equilibrium. Right, so if you have a charged conductor, right, and initially you put a lot of charge just kind of concentrated on one side, eventually, as time moves on, as they're allowed to move within the conductor, because they are able to do that because of a conductor's properties, then they will become evenly spread on the outside of the surface. So keeping that in mind, if we had a surface that looked like this, and our charges were at equilibrium, so they moved to the outside of the of the conductor, and you wanted to take the electric potential from this point A to B inside, what do you think the electric potential would be? It would be 0, because we have no charge enclosed on the inside. So no charge inside our conductors. I'm going to skip that example really quickly. So if you consider this spherical conductor placed in a uniform field, something unique happens. So because our field lines in our conductor point with our field, then this develops a more positive polarity at this side, leaving the other side to develop a negative polarity. And because of this, we know that electric potential flows from our positive, from our negative. So because of that, there's going to be a resisting field created from this induced polarity. And this only works for our conductors based on our properties that we know for it. So I hope that it makes a little bit of sense. This covers week 5 review notes for this lecture. So feel free to go over these concepts a little more. We covered how electric potential behaves in insulators and conductors, as well as talking about equipotential lines briefly. In the next video, we're going to be talking a bit more about these concepts and applying them in our Wiley Plus practice problems. So I will see you there.